Honored to present my talk in this session. Today, I will talk about gold nanoparticles and regarding the biodistribution and toxicity. So before talking about gold nanoparticles, I want to talk about regulatory issue in nanomedicine. So to release nanomedicine in the market, several toxicity studies and kinetic studies are essential. And regarding the toxicity studies, I think there is majorly two kinds of one. One is the mechanistic toxicity studies, which is usually performed by researchers to understand the mechanisms of toxicity and to decide the doses for GLP studies. And the other one is the GLP toxicity studies, which performed by GLP facilities according to the OECD test guidelines. So to be approved by the FDA, nanomedicine technology development pipelines has a very long period of time. So first one is the nanomedicine application in development. So it takes about 7 to 20 years, and which composed of basic research and preclinical animal studies. And after that, if the nanomedicines are confirmed as safe and effective, it goes into the clinical investigation. It took 1 to 7 years, and finally it come to on the market. So there is a huge huge needs for time and monies, and it is very difficult to be success as previous talk as discussed in previous talk. And for nanomedicines, there are many routes of administrations from the intravenous and intramuscular injections and so on. And among them, the intravenous injection is most popular, and many of the drugs has a route of administration as intravenous injection, and most of them are the passive targeting, not the active targeting. And then the light blue one is the investigational studies, and dark blue one is commercial studies. So many of them are the investigational status, not the commercial status. And when I searched gold nanoparticles approved or in clinical trial in US, there is two kinds of approved gold particles, and both are in vitro assays and not on the in vivo or invasive application. And 3-1 is in clinical trial. One is autoimmune, is targeting solid tumors, and the composition is gold nanoparticles and PEG conjugated, and also conjugated with TNF-alpha. And it is the phase 2 clinical studies. And the other one is Auditorium, is similar, but it is loaded paclitaxel, and is targeting solid tumors, and it is in the clinical study. And Auditorium is gold nanoshell, and it is targeting solid tumor, and application is post thermal therapy, because gold nanoparticles or gold nanorows can be applied for the thermal therapy. So there is a few kinds of gold nanoparticles in the pipeline, but among except for the biodegradable liposome or something, the biodegradable nanomedicine, among the harder nanoparticles such as metal oxide nanoparticles, some iron oxide and the gold nanoparticles are most popular. So to be approved by the FDA, there are several toxicity studies needed. So to give an example for GLP toxicity studies, I will show about the gadolinium-based ultra construct agent, and for the GADA-based, there needs PK studies with several kinds of animals, as the rats, rabbit, and dog and monkey, and also need a single intravenous injection study and toxicokinetics with the two kinds of animals. And also need repeated dose IV toxicity study and toxicokinetics. It needs, for the GADA-based, it has 4 weeks repeated dose IV toxicity study, but depending on the reviewer of the FDA, it can be a 90-day repeated dose toxicity study, and also it can be a carcinogenicity study, which needs injecting for 2 years, every 2 years, 2 years, sorry. And also, GADA-based needs genetic toxicology studies, Ames test, and chromosomal aberration test, and in vivo mouse micronucleus test, and reproductive development toxicity, local tolerance, and also for the specific for the gadolinium-based materials, there needs special toxicity because gadolinium-based materials can produce non-nephrogenic systemic fibrosis in rats. So basically, there are many kinds of toxicity. GLP toxicity studies are needed, and also special toxicology is also needed. So for the gold nanoparticles, I overview about the more than 80 reports on the in vivo biodistribution and in vitro cell-based toxicity studies. However, there are several discrepancies between studies which might be due to the differences of physicochemical properties of gold nanoparticles. And in this presentation, I will overview about the biodistribution and the toxicity of most popular gold nanoparticles, including the colloidal golds, sizing from 1 to 200 nanometer. And I will emphasize will be placed on the systemization of data of particle types and parameters and surface functionalization and route of exposure and dose applied and method of determination of gold nanoparticles. So for intravenous injection, this study was performed in our group. We used the 4, 13, and 100 nanometer size gold nanoparticles and conjugated with the polyethylene glycol and injected into the mouse tail vein and measured the gold levels by ISPMS at several time points from 30 minutes to 6 months. And we got several samples and measured the kinetics of nanoparticles. So for gold nanoparticles in blood showed very different patterns. In case of 4 and 13 nanometer size nanoparticles has a long circulation time. However, for 100 nanometer size gold nanoparticles has a very short blood circulation time, which means it is very well opsonized or phagocytosed by the reticular endocellular systems. And usually about after 1 day after injection, all particles were disappeared from the bloodstream. And for 4 nanometer gold nanoparticles in the tissues show that a very interesting pattern. They are accumulating until 6 months, and the major tissues are liver, spleen, and mesenteric lymph node. And other tissues has very low levels of gold nanoparticles, but the peak time for the concentration is about 24 hours to 7 days after a single injection. And for 13 nanometer gold nanoparticles, it shows very similar pattern with 4 nanometer gold nanoparticles. And the major target tissue is lung, spleen, and the mesenteric lymph node. And minor tissues are lung, kidney, heart, and testis and brain. And for 100 nanometer gold nanoparticles, it shows fast accumulation in the major tissues and retained until 6 months after a single injection. So it means when we injected with gold nanoparticles will stay in the liver, lung, liver, spleen, mesenteric lymph node for up to more than 6 months. And when we evaluated TEM, it showed that gold nanoparticles were engulfed by the phagocytes, such as Kupffer cells and spleen macrophages and lymph node macrophages, and show that they are located in the lysosomes. And we also, all particles, such as 4 nanometer, 13, and 100 nanometer particles were observed by the TEM images at 7 days post-injection. And excretion patterns showed very interesting because in the urine, we measured gold levels in the urine and the bile, and we found that the levels of the golds was very, very low. It means that they are hardly excreted. We also performed the different surface charge of the gold nanoparticles to evaluate the effect of surface charge on the kinetics of gold nanoparticles. We used the 15 nanometer gold nanoparticles and injected to mouse tail vein, and we also had a similar experimental settings. And we used the 3 types of gold nanoparticles: pegylated gold nanoparticles, and pegylated and carboxylated gold nanoparticles, and aminate gold nanoparticles, which give very different surface charges from 0 to negative charged and positive charged nanoparticles. So this is the TM images, and we confirm the functional groups by FTIR analysis. So when we evaluate total gold nanoparticles in mice by summing the gold levels in the tested organs, about 60 to 70% of initial dose was observed in the major organs, and until up to 24 hours after injection, it showed very different pattern. However, after 24 hours, it shows very similar pattern regardless of the surface charges. So the surface charges was effective for early time point, and after that, it shows similar patterns. So in case of the gold nanoparticles with pegylated and carboxylated particles has a longer, slightly larger the quantity than aminate one. It might be because aminate one enter into another minor organs. And the kinetics of gold nanoparticles in blood show that the pegylated gold nanoparticles has a long circulation time. However, the functionalized carboxylated and aminated one has a very short blood circulation time. And for tissue kinetics, when we measure the liver, the carboxylated one has the order of the quantity of gold was carboxylated, aminated, and pegylated. And after 1 day after injection, it shows similar pattern. And in spleen and lymph node and kidney also shows very differential the distribution by the surface charges, especially for lymph node. The differential effect was observed after 1 day after injection, which might be the location into the lymph node needs some delayed time. And for the lung and the heart and brain and tissue also shows differential kinetics distribution between the surface charges. And we also found the nanoparticles into the normal tissues and the lysosomes as well. And also when we evaluate the excretion patterns in the urine, the pegylated one and the aminated one has higher quantity than carboxylated one. However, in the bile, the carboxylated one has a higher quantity than others. This is another study performed by another group, which showed that they used the 33 nanometer colloidal gold, which was conjugated with pegylate PEG and TNF alpha, and they evaluate the tissue distribution up to 120 days after single injection, and found that the gold contents was consistently observed in the major organs, liver and spleen, and kidney was minor organs. And in the tumor-bearing mouse, it showed in gold nanoparticles does not much located in the tumors. They are located majorly in the liver and the spleen, and tumors has low quantities of gold. And this study was to evaluate the usually when we use gold nanoparticles, it is conjugated with the polymers. So he wanted to find out the core gold was separated with the coating polymers. So after the injection into the mouse, so gold nanoparticle cores was coated with amphiphilic polymers, and cores and polymer shells were labeled with radioisotope. And the purpose of this study was to know whether the in vivo polymer shell would remain around the cores or whether they would separate. So as a result, the ratio of radioactivity originating from radioisotope is shown for different organs at 24 hours after injection. So in case of the ratio of 198 gold with 111 indium shell the ratio is higher than 1. The polymer must have come off from the nanoparticle cores. So as a result, many kinds of the tissues has more than 1 values, which means the polymer coatings come off from the gold cores. And this study is to perform whether gold nanoparticles with nanoparticle composites, such as gold iron oxide composites, will be whether they are biodegrading or not. So So to evaluate the biodegradation of nanocomposites, they incubate nanoparticle with intracellular lysosomal environment because most of the particles injected into tailbane, they enter into the lysosomes, and in the acidic conditions or in the enzymatic environment, they are biodegraded. So for all types of, three types of nanocomposite, multi-core nanoparticles and the nanocubes and the gold iron oxide heterostructures, they shows the separating or biodegrading as time goes by. Look at this. This one shows the composite structure is intact at zero time point. However, after 90 days, it shows biodegradation, and nanocubes also similar patterns. They are biodegraded. And this study is performed 1 year fate of iron oxide coated gold nanoparticles in mice and showed that also similar patterns. The liver, spleen is the major target organ, and the polymer coated, the iron oxide gold nanoparticles, and PEG coated iron oxide gold nanoparticles both are have the accumulating propensity up to 1 year after injection, even though the distribution is slightly different by the coating method. And this is about the toxicity aspect performed by our group. When we injected the gold nanoparticles into the tailbane, it showed apoptosis in the liver tissues. However, it shows not much, it did not produce any inflammatory reactions. It showed only slight increases of apoptosis. So for the effect of size, although there are some discrepancies between studies, the consistent factors as follow. Smaller particles showed longer and widespread circulation time, and all gold nanoparticles showed accumulating propensity more than 6 months. And likewise, gold nanoparticles showed minimal excretion in both urine and bile. And most of gold nanoparticles were localized in the RES organs, reticuloendothelial organs, such as liver, spleen, and the mesenteric lymph node. And in the RES organs, the phagocytosed gold nanoparticles showed intact and no biodestruction, while iron oxide gold nanoparticles on polymer gold nanoparticle composite showed the biodegradation in the lysosomal fluid of phagocytes. In the 1 year study after single IV injection showed that the polymer coated and PEG coated gold nanoparticles were accumulated for more than 1 year. And gold nanoparticles showed minimal inflammatory reaction and produced apoptosis of phagocytes. However, but it is not much adverse effect. And for the effect of surface modification, the effect of surface modification on the kinetics of gold nanoparticles are not well understood, but the current results may imply that pegylated gold nanoparticles show the longer blood circulation time than the carboxylated or aminated one. And until 24 hours, the percentage of gold nanoparticles compared to the initial injected dose showed in order of carboxylated, aminated, and pegylated. However, it returned to similar levels after 24 hours. So the surface functionalization is only effective up to short term, like 1 day after injection. And the organ distribution of gold nanoparticles show the functional group specificity, but it is very difficult to which organs has free for which types of functionalization. And we also searched the oral administration of gold nanoparticles. This study was used radioisotope gold nanoparticles 198 gold nanoparticles, and feed it orally with using very different kinds of gold nanoparticles, and also that the translocation to circulation is very limited, less than 0.5%. So it is very difficult to enter into the systemic circulation, and the retention to organs is also very limited. So via oral administration, gold nanoparticles has very limited to entering into the systemic circulation. And this study is instilled gold nanoparticles into the lungs of rats. So for this study, they also used the 198 isotope gold nanoparticles coated with POS and 750 Dalton PEG and 10 kilodalton PEG. And also they found that the gold nanoparticles are retained into the lung. Not much fractions are translocated into the bloodstream. So for this slide shows that for the intratracheal installation, about less than 0.05% are translocated into the systemic circulation. However, when they were injected by intravenous, it shows a very high quantities observed in the bloodstream. And this study is inhalation of gold nanoparticles into the lung, and used 13 nanometer and 105 nanometer size gold nanoparticles, and inhaled those particles for 5 days, and recovered for 28 days with the ambient air, and found that 13 nanometer gold has high levels in the lung tissues. However, 105 nanometer has a very low concentration, which might be due to the aerodynamics of nanoparticles, because the bigger one has difficult to enter into the alveoli, and it is deposited in the upper respiratory tract, and it is easily cleared afterwards. And this study is instilled those 50 and 250 nanometer gold nanoparticles with a single lab particles and agglomerated one, and it showed that both single lab and agglomerated, and both size nanoparticles showed very minimal inflammatory reactions compared to very toxic particles, and the inflammatory reaction was very minimal. And for the dermal absorption of gold nanoparticles, this is not for gold study, but usually nanoparticles was known to it cannot enter into the penetrated human skin, intact skin. However, when the skins are damaged, it can enter into the systemic circulation. So for summary for oral lung skin exposures, the oral exposure of gold nanoparticles showed that minimal absorption, and although there are some differences between size and charge effect, it might be not big differences. And oral exposure of gold nanoparticles have no reports about the systemic toxicity as well as local toxicity. And pulmonary exposure of gold nanoparticles also showed long-term retention into the lung and minimal extrapulmonary translocation. And the retention rate in the lung is depending on the size, because it is related with aerodynamic properties. And both inhalation and installation of gold nanoparticles showed minimal inflammatory reactions, although huge amount of gold was retained in the lung, and they also agglomerated. And absorption of metal-based nanoparticles after dermal exposure is very limited, although some fractions can enter through the damaged skins. Thank you very much for your attention.